a few things. One, if you look at the overview, when I say next-gen technologies, things that come to my mind are, what will the next-gen products look like? What is going to be the next-gen technology landscape? I also want to talk about some interesting manufacturing challenges that are there. Not only that, I do want to go deep into manufacturing of some of these high-tech, next-gen technologies and products for health science. Of course, when I wanted to come up with a list of that, I had a lot of them, but we have only a short time frame, so I picked 4 of my best ones. I thought that if you're going to talk about medical devices, let's talk implants. And when I talk about implants, I want to talk about how we can manufacture a coronary stent implant. How can we bring high-tech technology to manufacture cardiac implant? How do we do intraocular eye implant manufacturing? And how to do a tissue implant. That's very exciting. That is the next cutting edge that's there for us. The landscape, the next-gen landscape that we're talking about, one thing that makes it very different than any other phase is the medical devices are becoming more and more intelligent. And what is it that makes them so intelligent? It is the fact that they are now contain embedded processors in them. And these embedded processors are becoming ubiquitous everywhere due to the decrease in size and due to the decrease in cost. And because of that, we have so many processors, they are becoming small, and the devices have those processors in them. And that's what makes them intelligent. So we always had intelligent devices, right? When I test blood sugar using a meter that goes in my pocket, it can talk to a central database in the cloud, so that if I use 4 medical devices to test blood sugar, one in my work, one at my home, and one in my car, they all talk to the same cloud. That's great. However, if we were to take it to the next frontier, what is it that we should do? We should take it from our pocket and put it inside our body. So that, to me, is the next frontier. So taking these devices, moving them inside your body as an implant is the next thing that I want to talk about. So the Internet of Things that we are now talking about will include, the vision for future will include these implantable devices that are inside us. And what makes these devices different from the outside? First of all, the size, right? We are talking about sub-micron, which is 10 raised to the power minus 6 or less meter devices. The other thing that makes them difference is, what are they made of? Not plastic, not polymers, not metal, but biomaterials. That's one of the things that is going to make it apart. It's our own biomaterial that is used to implant and build these devices. And so what is so different about all this? Now we need new manufacturing technologies to work with that. And that's what we are going to next see, how that changes. What are the challenges that these devices pose now for us? Some of them are, what does a manufacturing do? It takes science and converts that into product. It takes a molecule and converts it to medicine. It is manufacturing that takes what we build in a lab into the hands of consumers, or rather inside the body of consumers, because we're talking about implanted devices. So manufacturing has, because it is implanted, it has a very high bar that we never had before. So the manufacturing now has a higher bar than we ever had before, because we can't fail, because they're inside our body. And manufacturing has to overcome these challenges. So let's look at some of the challenges. And then as I talk about how we manufacture these 4 kinds of devices that I talked about, we'll look at it from the perspective of different challenges. Of course, there are numerous, but some of them that come to mind is precision. The size has become so small that the tools of yesterday no longer work for us. We need new machines, we need new robots, we need new, to build things of new demands of today's precision. The second thing is velocity. Now we are in a big hurry to bring them to market, and it is at the manufacturing that we can build the things that will make us to market with a high speed. The other challenge that is there is automation. There is no way we can build all this without automating the whole process. There is no way we can control the quality of what is happening unless we automate the whole process. So you will see that I have brought up automation as one of the big thrusts as I talk about how we are going to build these things. The other challenge is biological material. This is a new material. We never had that. Now we have a different kind of material. We have biological materials. This is the material from where my teeth will be made, my bones will be made, and my liver can be made. So this brings yet another challenge. So let us talk about how we can do that. The first one I said I will talk about is a coronary implant. So we are talking about a next-gen coronary stent implant. The picture that you see is that of a stent. We have had stents before for a while, but the next-gen stents are very different from the kind that we had before. Some of the things that are different is what you see on the right side is a simple mesh tube. It's a tube, as you can see, of a simple mesh, and this is placed inside a artery. An artery may be clogged, or an artery may just be weak, and you needed support from inside for it to keep open so that your body functions properly. How is that done? That is done by a stent, and that's why we take that tube and we put it inside that vessel. What is it that makes it different now than the stents of yesterday? We now have made of more durable material. We shouldn't have repetitive surgeries to remove stents and to put them again. So we are making it of a more durable material. The second thing that is different is it now contains drugs to reduce blood clots. That's amazing, because you don't have to worry about if as it is in the place where there is a problem and it is releasing drugs so that no blood is formed, then the chance of it having another problem is much reduced. The other thing that makes us different is they are self-expandable once they are in place. This is an amazing thing, because we need older stents need a balloon to guide it within the body. We use imaging technique to see is it going in the right place, and to remotely through a catheter put it, host it on top of a balloon and send it to the right place, and then expand it by putting air in the balloon. Instead of that, what you see here is self-expandable. It will just expand itself. So this is all very amazing as we look at the next frontier. So let's talk about how we can manufacture this, right? We are talking about next-gen coronary stent implant. I have picked this. It is a lathe. We all are familiar with lathes. We use lathe to manufacture. What is different about this lathe? It's a vasco lathe. Vasco from vascular. Of course, when we are talking vascular, we are talking about vessels, which means they are very thin, and it has some micron tolerances. It can work with very tight geometries. The size is very small, and it automates the material handling functionality. What does it mean? When it needs a certain material, it automatically brings it from place it is to where it is needed on the lathe surface. It also knows when it is running out of some material to automatically pick that up from the place where it is kept. So, or to raise an alert and say, after 50 more stents, we are going to run out of some material. So that's amazing. It also has something else. It has a direct drive leader ability, but it also has a rotary motion, and it puts the two together. So it takes the linear as well as the rotary motion, and that's what gives it the high performance to make coronary stent. The other thing is that the throughput becomes much faster as compared to the traditional screw-based lathes that we have. So these are some ways in which we do it differently. One other implant that I talked to you was cardiac implant. So implant, what is the next-gen cardiac implant going to look like? As you can see in the picture, it is something that goes in your heart. Actually, it can be anything. Cardiac is heart, implant is implant. Some of the cardiac implants that we know are coming up are pacemakers and defibrillators, or it could be any other device for that matter. So let's talk about manufacturing this. This is how next-gen cardiac implants are manufactured. There are various ways. I picked some next-gen examples. And this is the one that I want to share with you. As you can see, it is a hermesis system. What does that mean? What does it do? Anything that's in cardiac implanted in your heart is going to go inside. You have to seal it nicely in a shell casing. And when you seal it, you have to make the seal so solid that it doesn't open up. So here's this implanted, came home, by the way, something went wrong. What is happening? Oh, it opened up. Can't afford it. That was one of the problems that drove us to build better technologies to manufacture that. So how is that done? So the devices that are in that half shell enclosure, they are sealed hermetic seams weld. So what is this welding called? Instead of doing spot welding, where you just pick a few areas and you spot at different spots, you just weld them. That is a way to do it, but that happens. And you can't afford to have that in the heart. So this is a seam weld. So it takes a whole seam and it welds it. And then not only that, it also positions. There are special mechanics in the system that allows you to position the device during the laser welding. So the welding is done. It is done by a laser. And you know, laser is so sharp and needs such precision. You cannot make a mistake on positioning it when you are going to pass a laser to cut it. So that is, the mechanics is very special with the hermesis system. And not only that, after it is done, after the laser welding is done, there are a lot of post-processing steps that have to be done, typically. But with this system, they are programmed in it. So the kinematics to program that is right inside this system itself. So for every thing that you create, for every piece that is manufactured, the post-processing steps that are needed are also taken care of with the same system, with the same control. So that's also one thing that makes it easy to generate different kind of systems. The other advantage of this is that it has an automatic material handling, a load and unload cycle. And the good thing is the loading and unloading is in sync with the welding process. So as the weld is done, the loading comes to the right place and then it is unloaded. So these are some of the ways by which we are doing next-gen cardiac implant manufacturing. Another area that I want to touch upon is eye implant. So we have intraocular eye implant. What is an intraocular eye implant? It's really a contact lens, except that it stays within your eye. It doesn't come out. And you don't have to put it every day, it just stays. And it helps severe cases of cataract and myopia. So let's see how they are manufactured. So talk about some of the ways in which the manufacturing of eye implants, intraocular eye implants are improved. What you see here is a Lens Pro system by Aerotech. It is a lathe system, basically, and this is the lathe on which the contact lenses are built. Something very special about it. We have bearings, you know, we have ball bearings, and the bearings help us reduce friction. The special thing about this is it uses air bearings. So by using air bearings, we can minimize friction to almost zero. And when you can minimize friction to zero, then you can have ultra precision, because your precision is impacted by the friction that gets in the way of you building a device. So because of those air bearings, it is very precise. The other thing that is important is it does air isolation. Now what does the air isolation mean? When you are fabricating the lens, there is always some vibration in the background. The air isolation makes sure that the background mechanical noise gets in the way of building a perfect lens. So can you imagine I'm welding it with a laser weld, a contact lens, and somebody comes and shakes me, or there is a lot of vibration, somebody dancing here on the floor. Of course, it will be very inaccurate. Therefore, that ear isolation helps. The other thing that is important is, instead of using hydrostatic bearing, it really uses ear bearing and does it to the same quality. The other thing is, it is networked open control. That means the system that you see, they are networked. What that means is, if you today, a manufacturer needs to take out 100 a day, suddenly the demand changes and you need to do 1,000 a day. By this architecture, you are able to expand it very nicely because you can join more units with the same network. So that's one of the advantages. One good thing about this is the lens profile manager. It creates a G-code program. Why is the fact that it creates a G-code program important? It's important because G-code is a standard of working with CNC machines. You can program, everybody knows that. So the fact that it can standardize is one of the big steps. So if we have standards, if all the manufacturers are able to adhere to those standards and they have the same accuracy and precision, we are in for much better way, much more accurate, precise, and easily manufacturable items. So the last one. So this is about next gen tissue implants. So you see cyborgs. Why? Because two reasons really. The real reason, which I shouldn't be saying, is I'm a science fiction lover. I have to, it's like addictive. It's an addiction. So I wanted to put a science fiction picture somewhere, so I put it here. The second reason, the reason that I can pass it, that's how I convince myself, well, I think I can do it, is that this is the next gen we are talking about. So today we don't have real tissue implants, we don't really have a lot of people who are using it, so I couldn't give you a picture with a human being. So I brought in a picture with a cyborg. But this is the vision, that our bones, teeth, vessels will also be machine produced. And that machine production will be fabricated with biological materials. So how do we manufacture it? So the system I am showing you is called Organmo, and it has the ability to do tissue implant manufacturing. So we're using tissues to build body parts basically, and it's called biofabrication. Why biofabrication? Because it's fabricated. Why? Because a human biological material is used to do that. It's just like 3D printing. So, and that's used to manufacture the tissue. So what is happening here is that the material is deposited that consists of different biological cells that are just placed on top of each other. What is so unique about this as compared to every other technology that I spoke? Of course, one of them is obvious, it is biological, the other one not. But the other big thing is, everything else that I talked about was a subtractive manufacturing. That means you take something, you cut it with a laser. You cut to pieces, put them together on a welding machine. Or put them on a drill, put them on a lathe. And those are different ways of subtractive manufacturing. That means take a big piece, cut off what you don't need and create what you do. This is different. This is additive manufacturing. It's 3D technology, 3D printing technology is used to do that. That means you start with nothing and then keep adding layer after layer of biological material to create exactly what you need. And so they fuse together. And this machine can be used to manufacture vessels, bone, as well as teeth. And one thing that's really good about this, not only does it fabricate, because it's trial and error, because it is a cutting edge field, and because different bodies are different, and we have different ways to react to them. So not only does this system enable you to fabricate, but it can also do testing of the composite out of different compositions. So you can build multiple compositions and you can test them, do a comparative testing of them together. So these are some of the exciting things that I wanted to talk about. As you see, the next in technology, we have intelligence all around us. I am taking that to the next level and saying we want intelligence inside us. And I'm not talking about the natural brain, but implanted devices. Why is it possible to do that? Processors are smaller, cheaper, can go inside our body. We have manufacturing technologies that are coming up which can put them in our eyes as interocular, put them in our heart as a cardiac implant, put them in our vessels as a coronary, or build biological parts, which is next gen. So that is the vision that I have for future, and my excuse for picking that up is I am the Chief Technologist for Health and Life Sciences of Innovation in Hewlett-Packard. So naturally, it is of great interest to me to see that area of technology furthering. So while we talk about manufacturing, we have this opportunity to get together. I wanted to put in this pillar of medical technology, which will impact our life in a bigger way than anything else does. It's been a pleasure.